Okay, so what we're going to be talking about today is actually a very, very important idea that we're going to use in calculus. So just be sure that you do remember how to deal with partial fractions, especially when we get into calculus and we try to integrate, which right now you don't even know what integrate means, but once you get to it, there will be certain rational functions where we won't be able to find integral of unless we perform partial fractions. So they do play an important role. So today our goal is going to be literally to kind of figure out what partial fractions are and what it is exactly that this means, or what is it that we're going to do. So the goal of this section is to decompose a single fraction into the sum or difference of two or more fractions. So an example of this would be like if I give you a fraction such as 3x over 2x squared minus x minus 1. So I give you this rational function. This, for instance, decomposes to 1 over x minus 1 plus 1 over 2x plus 1, which this is known as the partial fraction decomposition of 3x over 2x squared minus x minus 1. So if we take a look at this, if you think back to algebra or some time ago, if you were given a fraction like this or an expression such as this, what your goal would be is to get a common denominator and get it to here to there. So if you think about it, we're kind of putting things in reverse now. We start off with this and we want to break it up into what it originally was before we kind of got the same denominator and put it together. Okay, so that's kind of, so if you're thinking, hey, we're kind of doing the opposite of what we've always been taught, that's exactly it. You know, it's like in the past, if I gave you something like this and I said simplify it, the first thing you'd say is, well, let's get a common denominator, put it together, and then it'll turn into that. So now we're saying, let's go back. Let's go back to the form that we had before we got the common denominator and put it together. Okay, so with that said, if we start off with any rational function, so if we say let capital R of x equal to P of x over Q of x. And so what am I doing here? I'm defining a rational function. I'm saying, look, let R represent a rational function where its numerator is a polynomial function divided by its denominator is a polynomial function. So what we're going to do now is we're going to say, okay, well, when can I perform the partial fraction decomposition on a rational function? And here's how we would know if we could perform a partial fraction decomposition. So if the degree of P of x is less than the degree of Q of x. So what are we saying here? The degree of the denominator is greater than the degree of the numerator. Then we can find the partial fraction decomp if it has one. So then here are the steps. So then the steps to finding its partial fraction decomposition are, so before we actually find the steps here, what we're going to do is we're going to say, okay, so if this is the case, we're going to follow these steps. Now, before we do that, one comment I want to make here is that if the degree of p of x is greater than or equal to the degree of q of x, then it's not that we can't perform the partial fraction decomposition. We need to do something first. And what we'll do is what we're going to use long division first. And what will happen is when we use long division, we'll get a whole kind of get like a whole number, not exactly a whole number, but a whole number variable expression, and then we'll have a remainder. So what will happen is, so when we use long division, and then the partial fraction decomposition can be performed on the remainder. So what we'll notice is, what I'm basically telling you is this: if the degree of the numerator is greater than the denominator or even equal, we can't perform partial fraction decomp yet. So more on this later, okay? So this comment I'm making, we'll do an example where you'll see this will be the case, and then we'll kind of talk about, well, how do I go about performing the partial fraction decomposition on this if possible? And I'll show you and we'll see that. But for now, what we're saying is, look, to perform partial fraction decomp, I need to make sure that the degree of the denominator is greater than the degree of the numerator. Okay, so if that's the case, then I could perform partial fraction decomp, and here are the steps. So the first step is going to be factor the denominator completely. So in other words, I'm saying factor this until you can't factor it anymore. Okay, so you need to completely factor the denominator. And then once you factor the denominator completely, here's where the tricky part comes along. So hopefully the second step makes sense to you. If not, I'm pretty sure it will make a lot more sense once we do some examples. Okay, so the second step is what's going to help us determine how to break up the fraction. Okay, so what's going to happen is now we're going to say break up the fraction into multiple fractions based on the classification of each factor. From step one. So what's going to happen is whenever you factor the denominator completely, each factor is going to have its own classification. Okay, so now what are these classifications? Well, let's get into the classifications. So here's what's going to happen. The first classification is that the factor that we're looking at, the factor is linear and it's non-repeating. So what does that mean if the factor is linear and non-repeating? Well, let me kind of show you. So here's what we're going to say. If the fraction is of the form, and here's what the form is, it'll be something like this. So you'll have like your numerator, whatever your numerator is. We care about the denominator, right? And what are we saying? We have a number x minus some number, Okay, so I'm saying that this is pretty much my factor, and then I'm going to have times some other factors, right? So I'm only focusing on this factor. Okay, so what do I notice? Why is this linear? Because if I have a number x minus a number, if I said, hey, graph this, and remember, these are just constants. If I said graph this, what would the graph of that be? It would be linear, right? Now, so what is it that we notice? That this factor is linear. Now, the other factors I don't care about, right? I'm only focusing on this factor. So this factor is linear, and it's non-repeating. How come? Because I only have one of them, right? So that's where the non-repeating comes from. I only have one of these factors. So if this number was something other than a 1, like if it was squared, then it would be repeating because I would have 2 of these linear factors. Okay? So if one of my factors is of this form, which this is linear and it's non-repeating, then this part, only this part would break up to, so then we would say, then the number x minus number, which is that factor, right? So that factor, this portion breaks up as the following. So we'll have our fraction over a number x minus the number, which that's our linear factor, and then this has other things that are also factored as. But just this part would break up to what? A over a number x minus a number. And then I'll have plus some other stuff. Now, what are the other stuff going to be? Well, it depends on all these other factors. So all I'm saying is this factor will just break up into that. Now, what's A? A is a constant. And what's our goal going to be eventually? Our goal is going to be to find that A, to figure out what A needs to be. Okay? So that's what's happening here for the linear case. Okay, so if it's linear non-repeating, the linear non-repeating part is going to break up like that. Now this plus the dot 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 stuff, that's how the other factors are going to be broken up. Okay, so now let's move on to the second case. Now what's the second case going to be? The second case will be, and let's actually go to the back page. The second case will be if the factor is linear repeating. Okay, so what we know is it'll still be linear. So here's what we're going to say. If the factor is of the form something like this, like we have whatever in the numerator, we don't care about, it's the denominator we care about. It'll be a number x minus any number. So notice how this is still what? A linear factor. But I have to the power of n. Now what do I notice? This is no longer non-repeating, it's repeating because how many of these do I have? I have n of them. Okay, and then I could also have some other factors in there, but this is the one that I care about. So we're going to say that then the number x minus number to the power of n portion breaks up as the following. So it'll be something like this. So we have our original fraction before we've broken it up, and then we have some other factors possibly, but this is what I'm focusing on. So this guy will focus on what? It'll be a over a number of x minus a number to the power of 1 plus b over a number x minus a number to the power of 2. And then what's happening, what are you noticing? My factor is staying the same as that, except what's happening to the power, I'm increasing it every time I go along. So it'll be plus c over a number x minus a number cubed, and plus, I'm going to keep doing this until I get to which power? To the power of n, which let's just say it'll be capital N over a number x minus a number to the power of n plus some extra stuff, which this extra stuff falls back to these other factors. But notice what happened. This repeating factor, what did I do? I wrote that factor what, n times. Now what did I do? I started with the power of 1, 2, 3, and then every time I went, I increased the power by 1 until I got to the power of n. Now, a lot of times I get asked the question, well, why are we writing this over and over and over until we get to n? See, our job, we don't know how many fractions this is going to have. Now, what is it that I do know? If I said, hey guys, starting from a over a number x minus number to the power of 1 all the way to n over the same factor to the number of n, power of n, if I said find me the common denominator, what would the common denominator be? It would be just, all of these would have the same common denominator as that guy. So then what is it that we're doing? We're listing all the possible fractions we could have where the common denominator would still be the same thing as whatever that factor is. Now, for example, if the second one doesn't belong, guess what will happen? When I solve for b, b will zero out. So we're going to make the most complete list, or all the possible fractions where my denominator is still the same, or my common denominator is still the same as this, and if there's any extra fractions, then the numbers, the a, b's, or c's, or whatever above is, what will happen is they'll zero out. So the problem is we don't know which ones zero out and which ones don't. So we're just going to make a list of all the possible fractions where when I get a common denominator and put them together, I'll get this factor out of it. Which, sure enough, because this has the highest degree, this is going to dictate what our common denominator is. Okay, so that's how the repeating just means we're going to have to relist that same factor, except every time we move along we're increasing its exponent until we get to the whatever that n is. Okay, so that's how the repeating case breaks up, which is similar to the non-repeating, except it just shows up multiple times. Okay, and it has the power and it keeps increasing. Okay, so moving on to the next case, which will be now the nonlinear. So what we're going to say now is, what if the factor is nonlinear, non-repeating? Okay, so what that means is the following. If the fraction is of the form we have a fraction here, and it'll be a number x squared plus a number. So what is it that we notice here? Now, why is this non-linear? Because if you were to graph this, what is a graph of something that's x squared plus a number? This is a parabola, and clearly we know parabolas are nonlinear. And sure enough, look, a number x squared plus a number, if I say try to factor this, you'll know that you wouldn't be able to factor this. So remember, we want to try to factor as much as you can. So what we're claiming is this can't be factored anymore, and so that's why this is now nonlinear. So how do we break this up? So if it's nonlinear, non-repeating, and we know clearly that this is non-repeating, how come? Because we only have one of these x squared plus a number, right? So how's this going to break up? So then the number x squared plus a number, so that factor, that portion breaks up as follows. So we'll have a number x squared plus a number to the power of 1. So just this part breaks up as ax plus b over a number x squared plus a number. Now notice how, why does the numerator become ax plus b? Because the denominator is what? It's a quadratic. It's a power of 2. So the numerator is always going to have an expression with degree 1 less than. So if we look at this the linear case, why are we just putting a? Because the degree of x is just 1, so that's why we're just putting constant. So if it's nonlinear, remember, it has to be of the form ax plus b. So the number x squared plus a number, above it you'd put ax plus b. And then obviously, since there's only one of them, I only need to put this once, plus, and then we'll have some extra statements based on what these other factors are. Okay, so remember, my focus is just this for now, right? So that's for the nonlinear. That's how the nonlinear breaks up. And it's safe to say that we're not going to go past our denominators when we factor them. It's usually going to be, the nonlinear is always going to be quadratic, so it's always going to be just ax plus b of that form whenever we have just an x squared in the denominator. Okay, so moving on to the last case, which, what is this? The factor is nonlinear repeating. And by now you probably can guess how you would break it up if it's repeating, right? It's very consistent with the linear repeating case. So we would say that if the fraction is of the form something like this, and we have a number x squared plus a number to the power of n, and then we have some extra factors. So this is what I care about, and notice we could see that this is clearly repeating because I have n of these. So then we would say that then the number x squared plus a number to the power of n portion breaks up as the following. So we'll have a number x squared plus a number to the power of n. That equals 2. So, and then obviously we have a bunch of these other things, factors here, right? So we could have factors. So that's going to break up as follows. So that will break up as ax plus b over a number x squared plus a number plus cx plus d over what's going to happen now, a number x squared plus a number to the power of 2. And I'm going to keep once again incrementing these until I get to what? Let's say I get to my power of n. So I don't know, let's just say it'll be lx plus n to the power or over a number x squared plus a number to the power of n, right? So it's, remember, I'm just starting from to the power of 1 and working myself to the power of n, and then we'll have some extra stuff. But this part literally just breaks up to that. And remember, if I said, hey, get the common denominator of this, what would the common denominator be? It would just literally be that guy, okay? So, and that's basically it. These are how we would classify them and how we would break them up, okay? So once we take each factor and we break them up, here comes kind of like the next part, which might seem a little kind of, you might be thinking, well, why am I doing all this work without thinking about what's going on? Or without really, it kind of seems like we're doing stuff that we shouldn't be doing. But here's the final step. So once the fraction is broken up, what we're going to do then is find a common. So now we're saying find a common denominator and write the fraction as a single fraction. So then you might be saying, well, then why did I break it up to begin with if I'm going to put it back together? Which, that's the thing, it kind of sounds counterintuitive, but there's a reason why we break it up first and then now we're putting them back together. And the reason is what? Our goal is to find the A, B, C, and D's that we were assigning in the numerator. So that's the reason why we're putting this together. Now, there is also an alternative way of solving this, which our book explains. So I don't mind which approach you take to find the constant in the numerator, but this is what I find kind of the easiest to work with. Okay, so once we put it as a single fraction, then what we're going to do is now we're going to then try to group. We're going to group like terms. So we'll group like terms together, and when we group like terms together, we are going to create a system of equations by comparing your fraction to the original. And when you start comparing this to the original, what you'll notice is then you'll be able to hopefully come up with a system. So then what will happen is then this system that we're talking about will allow you to solve for A, B, C, and so on in the numerators. Okay, so once you do that, once you're able to compare to the original fraction, and that system will allow you to solve for A, B, C, and so on, all the constants in the numerator, that will complete, which will complete the process of partial fraction decomposition. Okay, so basically what are we doing? Factor the denominator, then break up your rational function based on each factor in the denominator, whether it's linear, repeating, nonlinear, and so on, and then we're going to put it together. That's going to put it back together to help us solve for the constants in the numerator. And once we do that, that'll complete it. So let's look at our first example where we'll perform 3 partial fraction decomps. So for example 1, we're going to say find the partial fraction decomposition of, so for part A, we'll do 3 of them. So part A will be 13x plus 17 over x cubed plus 2x squared minus x minus 2. Okay, so starting off with this, let's go with the steps that we wrote. So what was the first step? Completely factor the denominator. And if we look at the denominator, it looks like we could factor that by grouping. And if you remember factoring by grouping, what did that mean? We would say, okay, what do these two have in common? They have an x squared in common. So if I factor out an x squared, what am I left with? An x plus 2. And then what do these two have in common? All they have is a negative 1 in common. So if I factor out a negative 1, then what will I have left? It'll be an x plus 2. And then what do you notice? This statement and this statement, they have an x plus 2 in common. So if I factor out an x plus 2, what am I left with? X plus 2, and then that becomes x squared minus 1. Okay, I'm not done completely factoring yet because the x squared minus 1, remember, I can't stop here and say, well, that's nonlinear because even though it is nonlinear, I notice that this factors further because x squared minus 1 factors to x minus 1 times x plus 1. So remember, we factor until we can't factor anymore. So this will be what? X plus 2, x minus 1, x plus 1. So what do you notice? Our denominator has 3 factors, and all 3 factors are what? They're all linear. And what do you notice about each one of them? They're all also non-repeating because I have 1 of each. So based on this information, we know that 13x plus 17 over x plus 2 times x minus 1 times x plus 1, what does that factor to? Remember, this x plus 2 is what? Linear non-repeating, so that will break up to what? A over x plus 2. So this guy is taken care of. Then I'll say plus, now go on to the next factor. What do we notice? This is linear non-repeating, so that will be what? Since A has already been used, we'll say B over x minus 1. So that's taken care of. And then finally, when I get to this one, that's also linear non-repeating, and it'll be C over x plus 1. Okay, so now that we have this, what is it that I want to do now? Now we want to grab this and get a common denominator, put it all back together, and then when we put it back together, we want to compare the right side to the left side because they need to both be the same. So to get a common denominator, what is this guy missing? It has an x plus 2. It needs an x minus 1 times x plus 1. So I'll multiply top and bottom by x minus 1 times x plus 1. x minus 1 times x plus 1. And then this guy is missing what? An x plus 2 and an x plus 1. And then multiply the top by an x plus 2 times x plus 1. And then what's this guy missing? An x plus 2 times x minus 1. So now look at what's happening here. My denominators that I have is what? Now matching with the denominator on the left side. So since my denominators are matching, I'm just going to start ignoring them. Now what do I need to make sure? I need to make sure my numerators match. So even though I'm not going to write the denominators from this point on, it's not that I'm just like, it's not like they're gone or they've disappeared. It's just I'm ignoring them because the denominators are matching up. All I care about is what now? The numerators. So I'm going to say now, what do we know? 13x plus 17 equals to, what happens here if I multiply this out? X minus 1 times x plus 1, that becomes, and I'm going to distribute the a as well. So that'll be what? A times, I'm just multiplying this out, which would be x squared minus 1 plus b times, what's x plus 2 times x plus 1? That'll be x squared plus 3x plus 2. And then plus c times, what's x plus 2 times x minus 1? That's x squared plus x minus 2. Now, we're going to distribute the a, b, and c. So then what do we have? 13x plus 17 equals to ax squared minus a plus bx squared plus 3bx plus 2b plus cx squared plus cx minus 2c. Okay, now that I've distributed these, what my goal now is to pretty much group all the like terms. And what are my like terms? It's all the variables. So when I group all the x squareds, or when I'm trying to combine the x squareds, I want to go after everything that has an x squared. So what do I notice here? We have 13x plus 17 equals to, so as far as the x squareds go, I have the ax squared, bx squared, cx squared. So what I'm going to do is I'm going to put them together and I'm going to factor out an x squared. Okay, so hopefully you understand what I'm doing. So from here on out, these are my like terms, which if I bring them down and I factor out an x squared, what is that going to be? It'll be a, right, because I have an a here, plus b, plus c times x squared. So what I did is I just grouped these together and I factored out an x squared. Okay, so the constant in front of my x squared is what? It's a plus b plus c. Then plus, let's look at our x's. I have a 3bx here, and what else do I have? A cx. And then I think that's basically it. So my x's are 3bx and cx. So if I put them together, it'll be a 3b plus c, and I've just factored out an x from them. Okay, hopefully you're following along. If not, always don't hesitate to message me and let me know where you got stuck. And then the ones that don't have x's, those are just my constants. So what do I have? I have a plus negative a plus 2b and minus 2c. Okay, now here we have it. So what is it that I notice here? Based off of this, now look, now I need to compare the right side to the left side. Now look, in front of my x squared, I have a what? A plus b plus c. Now when I look at the left side, do I have an x squared? And if you look at this, clearly I don't have an x squared on the left side. So what does that mean about the a plus b plus c? I want this, I want a plus b plus c to equal to what? I want that to equal to 0, right? Because how come? Since there's no x squared here, I need this x squared to go away. And the only way it'll go away is if what? If a plus b plus c is 0. Okay? Now, using that same argument, what do I notice here? The number in front of my x here is what? 3b plus c. And if I look at the left side, what's the number in front of my x? It's 13. So if I want the left and the right side to be equal, the 3b plus c has to equal to what? 13. Okay? And then my last term, which these are what? My constants, right? Because notice how this doesn't have an x, which the negative a plus 2b minus 2c, what must that equal to? This must equal to 17, because that's my constant. Now that we have our system of equations, now what could I do? I could solve for basically a, b, and c. Okay, and you could use any method you want. So since this is 3 equations, 3 variables, what could I do? I could say now this becomes kind of what we did in section 2. You could say row 1 plus row 2. And if I do that, how come? Because I notice that these are opposites. So I get a plus b plus c equals to 0. And then 3b plus c equals to 13. And then that becomes what? That zeroes out. Sorry, this is supposed to be row 1 plus row 3, not row 1 plus row 2. All right, so that'll zero out, and then b plus 2b becomes 3b, and then c minus 2c becomes minus c, and then 0 plus 17 is still 17. And then what do I notice? Row 2 and row 3 are the same, so I'll just say negative row 2 plus row 3. And if I add that, what do I get? I get a plus b plus c equals to 0. 3b plus c equals to 13. And then what happens here? Negative 3b plus 3b, that goes away. Negative c plus negative c is minus 2c. And then negative 13 plus 17 is 4. So notice how I could solve for c now. So what does that imply? C is negative 2. And if c is negative 2, I could plug it in here. And what does that give me? 3b minus 2 equals to 13, which implies if I add 2, I get 15, which implies b is 5. And if b is 5, then what do I have here? We know that a plus 5 minus 2 equals to 0, which implies what? A would be negative 3. Okay, so now that I found a, b, and c, now I could write my partial fractions. And what is my partial fraction? If I go back to my original partial fraction, what was it? It was a over x plus 2. So what's a here? It's negative 3. So my answer is negative 3 over x plus 2 plus, and then what was b? It was b over x minus 1, and then b is what? 5 over x minus 1. And then lastly, it was c over x plus 1, and c is negative 2, so it'll be plus negative 2 over x plus 1. And see, these are my partial fractions. In other words, what am I saying? If we combine these, get a common denominator, and add them together, I'll get that back. Okay, so this is my partial fraction decomposition of that fraction right there. Okay, so with that said, let's look at the second example, which is just part B of example 1. So let's find the partial fraction decomp of something like this, which is 6x squared plus 6 over x times x minus 1 cubed. Okay, now if you look at this, what do you notice? This is already completely factored for us, which is good, so we don't have to factor it. So we can go ahead and start breaking this up. And if I break this up, how is this going to break up? It'll be, so that's just x, which is linear, and I have only one of it, so it'll be just a over x plus, now what is this? This is linear, but it's repeating, and I have how many of them? 3 of them. So how would that break up? So the x has been taken care of. So what would this be? This would be b over x minus 1. And then I'm going to keep going until what? The x minus 1 is the factor, right? Except I'm going to then have to go until I reach x minus 1 cubed. And it'll be what? Plus c over x minus 1 squared plus d over x minus 1 cubed. Okay? So there you have it, and that's taken care of. So remember, for the repeating ones, we start with the factor to the power of 1, and then we keep working its way up until we get to whatever that number is, which is 3. So once we have this, now we want to get a common denominator and put these together. So what's this guy missing? It's just missing an x minus 1 cubed, and then that's an x minus 1 cubed. What's this guy missing? It's missing an x times x minus 1 squared, x times x minus 1 squared. This guy's missing an x times x minus 1, x times x minus 1, and this guy's missing just an x. Now remember, when I'm multiplying these out, my denominators are already matching up because the denominator here is the same as the denominator there. So now I'm going to turn my attention to the numerators. So 6x squared plus 6 equals to, what's x minus 1 cubed? That would basically be, if I were to multiply it out, it'll be what? Let's come off to the side and do this. So x minus 1 squared is just x squared minus 2x plus 1 times an additional x minus 1, which gives us x cubed minus 2x squared plus x minus x squared plus 2x minus 1. So this guy, x minus 1 cubed, ends up being what? A times x cubed minus 3x squared plus 3x minus 1. Okay? And then plus, what's x times x minus 1 squared? That'll just be what? X cubed minus 2x squared plus x. So all I'm doing is I'm just multiplying these guys out, right? That's multiplying these out. Plus c times x squared minus x plus dx. Now let's distribute the a, b's, and c's and d's, and then let's start comparing them to the left side. So we have 6x squared plus 6 equals to ax cubed minus 3ax squared plus 3ax minus a plus bx cubed minus 2bx squared plus bx plus cx squared minus cx plus dx. Okay? So now let's combine like terms. So 6x squared plus 6 equals to, so the x cubes, what do I have? I have an a plus b, and that's it, right? So it'll be a plus b times x cubed plus, for the x squareds, what do I have? I have a minus 3a minus 2b plus c x squared. All right, so that's that. And then for my x's, what do I have? I have a 3a, and then what else? Plus b minus c plus d x. And then for my constants, oh, this might be nice. I just have what? A minus a. So here's what we know. We know for a fact that what? The a plus b has to equal to what? If you look at the left side, there is no x cubed, so clearly we want this to go away, so a plus b has to be 0. And then what else do we have? We have the minus 3a minus 2b plus c equals to, now the number in front of x squared has to be a 6. Okay? And then the number in front of the x, which is 3a plus b minus c plus d, that has to equal to what? That also has to equal to, so since there's no x here, that also has to be 0. And finally, what do we know? Minus a, which that's just my constant, that has to equal to 6. Now what's the good news? We get a for free, right? So what does that mean? A equals to negative 6. And if we get a for free, then we pretty much get b also, don't we? Because if a is negative 6, what does that mean? Negative 6 plus b equals to 0, which means b is 6. And if b is 6, what we notice here, which is beautiful, we get c for free, right? Because what do we have? Negative 3 times a, which is negative 3 times negative 6, minus 2 times 6, because of b, plus c equals to 6. So now I could solve for c, which would that be? 18 minus 12, which becomes 6. Is that right? 18 minus 12 is 6. And then if I subtract the 6, which, what does c become? C becomes 0. C is 0. Okay? And then lastly, I could get what d is. So what do I know? A is negative 6, so it'll be 3 times negative 6, plus b is 6, c is 0, so that's gone, plus d equals to 0. And then what do I have? Negative 18 plus 6 is negative 12. If I add 12, then d is 12. Now look at what happened here. My partial fractions are what? A over x. So what's a? A is negative 6 over x plus b over x minus 1, which what is b? B we found to be 6, so it'll be 6 over x minus 1 plus, now look at what happens here. We had c over x minus 1 squared, didn't we? But what's c? C is 0. So guess what? This fraction wasn't a part of our partial fractions anywhere. So remember how I said earlier, we're going to write all the possible combinations. If one doesn't belong, it'll 0 out. So in this case, that one didn't belong. And then what was d? D was 12. So it'll be 12 over x minus 1 cubed. Now there's my partial fraction for this problem. Okay? So let's look at one more partial fraction problem, and then we'll do one final example, and that'll wrap this up. So for part C, we're going to say this is 11x squared minus 2x plus 24 over x cubed plus 4x. Okay, so let's factor out the denominator, which becomes what? 11x squared minus 2x plus 24. And what was it that we have? We could factor out an x. And what are we left with? An x squared plus 4. And sure enough, and I can't factor any further because x squared plus 4 doesn't factor anymore. So what do I notice? Linear, non-repeating. This is what? Nonlinear, non-repeating. So how would this break up? The 11x squared minus 2x plus 24 over x times x squared plus 4. What does that break up? This one is what? Linear, non-repeating, so it'll be a over x plus, now this is nonlinear, non-repeating, so that one's been, we took care of that there. To take care of this, what would that be? It'll be x squared plus 4 in the denominator, and if you remember what would be in the numerator, it would be a linear function. It would be 1 degree less than this. So if this is x squared, the numerator would be what? Bx plus c. Okay? Now, and that's taken care of. Now remember, if this were repeating, then I would continue doing this, right? But now we fall back to what we did for the next two examples. What do I want to do now? Get a common denominator. So this guy's missing an x squared plus 4. X squared plus 4. This guy's missing an x. And when I do that, once again, my denominators are matching up, so I'm going to turn my attention to the numerator. So what happens to my numerator? It'll be 11x squared minus 2x plus 24 equals to, if I distribute the a, what do I get? I get ax squared plus 4a plus, if I distribute this x, what do I get? I get bx squared plus cx. Okay, so now let's combine like terms, or put like terms together. The ax squared plus bx, so that becomes what? A plus b x squared. And then plus, we have just a cx, that's the only x we have, and we have plus 4a. So I think this one's actually going to work out really nicely because look, we should get a and c for free. So what's a plus b? Well, a plus b is in front of this x squared, and what's the number in front of this x squared? It's 11. So a plus b has to be 11. Now, how about c, which is the number in front of x? Well, if I look over here, what's the number in front of x? It's negative 2. So notice how we got c for free, okay? And then what do I have now? 4a. And 4a is just my constant. And what does 4a have to equal to? 24. And if 4a is 24, what does that imply? A must be 6. And if a is 6, then I could easily find b, which becomes what? 6 plus b equals to 11, which implies b is 5. And there you have it. So what's my partial fraction for this look like? It was a over x, which a is, we said was 6. So it'll be 6 over x plus, then it'll be bx plus c. b was what? 5. So it'll be 5x plus c, except c is negative 2. So I'll say minus 2 over x squared plus 4. And there's my partial fraction. Okay, so hopefully this doesn't sound too bad, and you'll only get better through practice. But we did an example where we saw kind of almost of every type, right? The only thing we didn't see was the nonlinear repeating case, but I'm pretty sure you could figure out how to go about that. Okay, so the last example I want to do, which has to do with, well, what if I have a fraction? So for example 2, and then this is where we'll end this. So prepare the following for a partial fraction. So for partial fraction decomposition, which is x to the 5th plus 3x squared minus 5 over x cubed minus 4x. Now see, if you look at this right now, what's the problem? If you tried to perform partial fraction decomposition on this, it wouldn't work. How come? Because remember, to be able to use partial fraction decomp, the degree of the denominator must be greater than the numerator. Now notice over here, the numerator's degree is greater than the denominator. So remember earlier on I said, well, if this is the case, we might still be able to use partial fraction, but to do so, we first have to perform long division. So what am I going to do here? I'm basically going to say x to the 5th, and then plus 0x to the 4th. These are placeholders, right? Plus 0x cubed plus 3x squared plus 0x